Hey everyone, welcome back. Or if you're just joining us, welcome to KSSP Podcast. I'm Spencer.
I'm Katie.
And in this episode of our Stars Life Cycle series, we're gonna be talking about average stars and massive stars. So we'll just kind of start with an average star. And average stars are also known as intermediate mass stars. These stars have lifetimes between 50 million and 20 billion years. These stars generate energy from the fusion of hydrogen to helium, then helium to carbon. And just in case you weren't aware, our sun is an average size star.
Any star which is larger than 8 solar masses during its regular main sequence lifetime is considered a massive star, and they typically have a quick main sequence phase, a short red supergiant phase, and a spectacular death via supernova explosion. In a massive star, hydrogen fusion in the core is followed by several fusion reactions involving heavier elements. Just before it exhausts all sources of energy, a massive star has an iron core surrounded by shells of silicon, sulfur, oxygen, neon, carbon, helium, and hydrogen. During the expansion, a dense layer of gas and dust is collected around the HII region, after which gravitational instabilities in the layer cause it to fragment into dense clumps, which then go on to collapse into new stars. The fragments are massive and thus form massive objects, stars or clusters. Although they're extremely rare, comparing less than 1% of the total stellar population, they make their presence known by dominating the surrounding interstellar medium with the powerful stellar winds as well as shocks from their eventual supernova.
And then I just have a little thing here from NASA. It's a evolution of a massive star. So as we can see, protostar to a yellow bubble. So this series of images show 3 evolutionary phases of massive star formation from NASA's Spitzer Space Telescope. The stars start out in a thick cocoon of dust, evolve into hotter features dubbed yellow balls, and finally blow out cavities in the surrounding dust and gas, resulting in green-rimmed bubbles with red centers. So this process shown here takes roughly a million years. Even the oldest phase shown here is fairly young, as massive stars live a few million years. Eventually, the stars will migrate away from their birth clouds. So
Yeah,
there's that
we gotta
picture there.
remember that what we're viewing now is what happened like probably at least millions of years ago, if not billions, just because of how far away this stuff is in light years.
Yes.
So, like, this isn't happening right this second. This already happened, what we're viewing.
Yeah, yeah. And yeah, that's interesting too. An
Yeah.
interesting fact or thing, I guess, to
It,
consider when viewing image or even just talking about any of that
like,
stuff
what's going
too.
on in space and stuff.
Yeah.
Yeah, I agree. And I did have the life cycle of our sun in an article as well. So, our sun is a perfectly normal example of a G type main sequence star, G2b, aka yellow dwarf. And like all stars, it has a lifespan characterized by a formation, main sequence, and eventual death. So the lifespan began roughly 4.6 billion years ago and will continue for another 4.5 to 5.5 billion years when it will deplete its supply of hydrogen, helium, and collapse into a white dwarf. But this is just the abridged version of the sun's lifespan. So the sun is about halfway through the most stable part of its life. And it's remained relatively unchanged This will stay the case for another 4 billion years, at which point it will have exhausted supply of hydrogen fuel. When that happens, some pretty drastic things are going to take place. So, according to nebular theory, the sun and all planets of our solar system began as a giant cloud of molecular gas and dust. Then, about 4.57 billion years ago, something happened that caused the cloud to collapse. It could have been the result of a passing star or shock waves from a supernova, but the end result was a gravitational collapse at the center of the cloud. So the pockets of dust and gas began to collect in denser regions. So as denser regions pulled in more and more matter, conservation of momentum caused it to begin rotating, while increasing pressure caused it to heat up. Most of the material ended up in a ball at the center, while the rest of the matter flattened out into a disk that circled it. The ball would eventually be called the sun, while the disk material would form the planets. The sun was a collapsing protostar for about 100,000 years, before temperature and pressures in the interior ignited fusion at its core. The sun started as a T Tauri star, wildly active star that blasted out an intense solar wind, and just a few million years later, it settled down into its current form. So every second, 600 million tons of matter are converted into neutrinos, solar radiation, and roughly 4 times 10 to the 27th power watts of energy. For the sun, this process began 4.57 billion years ago, and it's been this way ever since. And as we talked about, there's a finite amount of hydrogen in the core of the sun, so it's not going to last forever. And the sun has been converted an estimated 100 times the mass of the Earth into helium and solar energy. As more hydrogen is converted into helium, the core continues to shrink, allowing the outer layers of the sun to move closer to the center and experience a stronger gravitational force. And this places pressure on the core, which is resisting by resulting increase in the rate with which fusion occurs. So the sun continues to expand hydrogen in its core, the fusion process speeds up and the output of the sun increases. So it leads to a 1% increase in luminosity every 100 million years and 30% increase over the course of the last 4.5 billion years. So in roughly 1 billion years, the sun will be 10% brighter than it is today. So Earth's atmosphere would absorb that heat energy, and it would trigger a moist greenhouse effect here on Earth, similar to what happened to Venus, looks like. And in 3.5 billion years, the sun will be 40% brighter than it is now. The oceans will boil, the ice caps will permanently melt, and all water vapor in the atmosphere will be lost to space. You know, if we don't just do that ourselves first with global warming, but that's fine. Under these conditions, life as we know it won't be able to survive. And so it would be similar to Venus. Let's see, the core hydrogen exhaustion. With its hydrogen exhausted in the core, the inert helium ash that built up there will become unstable and collapse under its own weight. This will cause the core to heat up and get denser, causing the sun to grow inside and enter the red giant phase of evolution. So the sun would grow large enough to encompass the orbits of Mercury, Venus, and maybe even Earth. And then, of course, even if Earth survives, the heat's going to scorch our planet from that, so... and the final phase in death. So once it reaches the red giant branch phase, the sun will have about 120 million years of active life left. But a lot's going to happen during this time. The core will ignite violently into a helium flash, where 6% of the core and 40% of the sun's mass will be converted into carbon within a matter of minutes. The sun will then shrink around 10 times its current size and 50 times its luminosity, with a temperature a little lower than today. And then for the next 100 million years, it will continue to burn helium in its core until it's exhausted. And then it would be, after that, it would be an asymptotic giant branch phase, where it will expand again much faster this time and become more luminous. In over 20 million years, the sun will become unstable and begin losing mass through a series of thermal pulses that'll occur every 100,000 years. They'll become larger each time and increase the sun's luminosity to 5,000 times its current brightness and its radius to over 1 AU. So the post-AGB evolution will be even faster as the ejected mass becomes ionized to form planetary nebula and the exposed core reaches 30,000 Kelvin. The final naked core temperature will be over 100,000 Kelvin, after which the remnant will cool towards a white dwarf. The planetary nebula will disperse in about 10,000 years, but the white dwarf will survive for trillions of years before fading to black. The ultimate fate of our sun. Our sun's not massive enough to make a supernova or a black hole. So, given its mass, our sun will eventually collapse to a white star until it burns itself out. And of course, this won't be happening for another 6 billion years or so. And then by that point, humanity will either be, dead or have moved on from Earth. So we have plenty of days of sunshine to look forward to, it says. Lovely.
So, now that we've discussed kind of average and massive stars, in the next episode, we're going to move on to red giants and red supergiants. And as always, you can leave a comment below letting us know if there's any topics you want us to go over in future episodes.
Yeah, you can reach out to us on Facebook, YouTube, Instagram, Twitter, TikTok, and we do occasionally do Twitch live streams.
And don't forget to like, follow, or subscribe, and turn on notifications so that you know when we do. Otherwise, we'll see everyone in the next episode.